Hi everyone. In this video, we are going to take a closer look at isotopes and average atomic mass. So the goals of this video are to help you understand isotopes and isotope notation, to understand similarities and differences in the properties of isotopes, and then begin to calculate average atomic mass given relative abundance information. So as we talked about in class today, we know that the atom consists of three separate subatomic particles, right? We have protons, neutrons, and electrons. Protons and neutrons are in the nucleus, and electrons are outside, right? So protons and neutrons have relatively the same mass, and they're stuck together in the nucleus. So we end up with this nucleus that contains protons, which I'm drawing here in red, and neutrons in blue, and these guys are held together by that strong nuclear force. And then we have these electrons out here on the outside, right? And we said that the protons and the neutrons determine the mass number of the element, so the mass number or the mass of the element, and the protons have to equal the number of electrons if it's neutral, but we can make it an ion by changing the number of electrons, right? So if I'm adding or subtracting electrons, I'm making it an ion. If they're neutral, the number of protons and electrons have to equal each other, and the protons plus the neutrons, the number of protons and the number of neutrons determine the mass number or the mass of the element, right? And this thing, okay, so recall that we also said that it's the atomic number or the number of protons that determines what element an atom is. So if an atom has one proton, no matter what else is true about that atom, it is an atom of hydrogen. So when we look at changing the number of neutrons, like so for example, if we have a proton, hydrogen here, right? Hydrogen itself, this guy right here, has one proton. Most hydrogen doesn't have any neutrons, but there are atoms of hydrogen that have one proton and one neutron, or one proton and two neutrons. So the only thing that's changing here about these atoms is the number of neutrons. So it's the mass that's changing. This one has a mass of 1, and this one has a mass of 3. So these three things that we're showing here, hydrogen, deuterium, and tritium, are called isotopes. These are isotopes of hydrogen. So an isotope they're atoms with the same number of protons, so the same atomic number, but different masses. And that different mass comes from the number of neutrons, so they have a different number of neutrons. Now, the presence or absence of these neutrons doesn't really change anything chemically about the atom. So if I have atoms of the same, isotopes of the same element, these guys are chemically identical to each other. Remember, it's the electrons that determine chemical behavior, not the nucleus. They do have different masses, right? Because of the different number of neutrons. And some of them, the nucleus might be unstable, making that particular isotope radioactive. So things are radioactive if they have an unstable nucleus. But remember that radioactive nuclei have the same chemical properties as stable nuclei of the same element, right? So for example, if I have an isotope that's radioactive, like say for example, carbon-14 is radioactive and carbon-12 is not, it's stable. Carbon-12 and carbon-14 are chemically identical to each other. They react in exactly the same way. The only difference is that one has a couple extra neutrons and will eventually, will undergo a nuclear reaction and to become more stable. Okay. What you're seeing here on the bottom is the chart of isotopes. There are a lot of naturally occurring isotopes. So to help us keep track, we have something called a chart of the nuclides or chart of isotopes. And on the x-axis here is the number of protons. So this is the atomic number. And on the y-axis here is the number of neutrons. So as we go across a row, I know it's hard to see because it's kind of tiny. So as we go, anything that's in the same column, so we circle here in the same column, those represent isotopes of the same element, right? Because remember, the same element needs to have the same atomic number, but the number of neutrons will be different. So there are notations here that represents, like, so for example, the If you look at this closely, the black ones represent stable isotopes. The red ones represent things that undergo a specific kind of decay versus the blue ones, a different kind of decay. But there's lots and lots of different isotopes here. Some are stable, some are not. We're really only going to be concerned with stable isotopes from here. So if we're looking at stable isotopes and things that change based on mass. So remember, the only thing that's different about isotopes is the mass. We need to think about how we can measure or think about atomic mass, right? So atomic mass is measured in a unit called the atomic mass unit. So the unit for mass, atomic mass, is the AMU, which stands for atomic mass unit. And it's defined as, so 1 AMU is equal to exactly 1/12 the mass of a carbon-12 atom. Okay, so what that means is that carbon-12 weighs exactly 12 point lots and lots and lots and lots and lots and lots of zeros AMU. Okay, so that makes 1 AMU slightly less than the mass of a proton or a neutron. So you'll notice that we had it on the chart before, but 1 proton weighs approximately 1.007 AMU, and 1 neutron weighs approximately 1.009 AMU, which we are going to round to be 1. So for our purposes, right, we're going to take the mass number, and that mass number is going to be pretty darn close to the mass in AMU. So we're going to say that the mass number equals the mass in AMU. So if I have, for example, a carbon-14 atom, carbon-14 has a mass of 14 AMU. So given that we have elements, we have these isotopes, and they're chemically identical, there's no way for us to separate out isotopes based on mass. If I were, for example, to have a sample here, let's say that I have a sample of chlorine gas, right? My chlorine gas is going to have different isotopes in it. So let's say that this is, the red is one isotope and the blue is a different isotope, right? So there's lots of different isotopes in here with different masses. And my question is, on average, how much does one atom of chlorine weigh? So how much does an atom of chlorine weigh? So if I were to pick out all of these atoms, like one at a time, on average, how much would it weigh? In order for us to figure this out, we need to know a couple of things. We know that chlorine has 35 two naturally occurring isotopes. They're chlorine 35 and chlorine 37. 75.78% of chlorine is chlorine 35, and 24.22% is chlorine 37. Okay. So just like with the penny activity that we did in class, we need to take into account how much of each isotope is present so that I can figure out, on average, how much does an atom of chlorine weigh. So the way that we're going to do this is to take a weighted average. All right. So we're going to say that the average mass is going to be equal to the sum of the mass of the isotope times its relative abundance. And you want this abundance in decimal form, by the way, not percentage. So times its relative abundance, and we do that for each isotope, and then we add them together, and we're going to get an average mass. So for chlorine, given the data that I have up there, right, I know that the mass of the isotope of chlorine 35 is going to be approximately 35 AMU, right? So 35 AMU times its relative abundance, which is 75.78%. But I want that in decimal form, so I'm going to divide that by 100, plus 37 AMU, which is the mass of the other isotope, times 24.22%, again, divided by 100 because I want to get rid of that percent. And when I put that in my calculator, what I'm going to get is 35.48 AMU. Okay. Now, if you look at the average mass that's on the periodic table for chlorine, you'll notice that that average mass is a little bit lower than what we actually calculated. And that has to do with the assumption that we're making, whereas that says that this isotope weighs exactly 35 AMU. It doesn't. Remember that there's some mass that's lost to binding energy, and some other, we rounded that AMU, so it's not quite equal to 35 AMU. So the mass on the periodic table was 35.45 AMU. That's pretty close, and we'll take it. Okay, so given that we can now take a weighted average to calculate the average atomic mass of a particular element, give this next problem a try. So sulfur is 3 stable naturally occurring isotopes. You have their information is given to you there. Give this problem a try. Try it in your packets, and then bring it with you to our next class where we will go over it then. All right. Thanks, and I'll see you in class.